Imagine a world where the average temperature is negative 60 degrees Celsius. The air is unbreathable, and deadly radiation constantly barks the surface. This isn't a dystopian movie, it's Mars. For decades, humanity has dreamed of colonizing the red planet, but the reality is a brutal test of engineering and human resilience. Can we truly build a self-sustained home there, or is it an impossible fantasy? Everything is a system. In grade 12, understanding complex interdependencies is crucial, and few systems are as intricate as a self-sustaining human colony on Mars. Dr. Aris Thorne, a lead astrobiological engineer at NASA's Jet Propulsion Laboratory, explains that for a Mars colony to survive, it must master in-situ resource utilization, or ISRU. This means living off the land, extracting vital resources like water from subsurface ice reserves and oxygen from atmospheric CO2 availability. Every breath, every drop of water, every calorie of food depends on cleverly engineered systems that transform Martian resources into human necessities. Protecting colonists from extreme radiation exposure levels and maintaining habitat structural integrity are equally paramount. Without these core components functioning seamlessly, life on Mars is simply not viable. Our Mars colony system has 10 critical components. 4 are external inputs: solar energy input, atmospheric CO2 availability, subsurface ice reserves, and radiation exposure level. The 6 internal outputs, which our colony must produce and manage, are oxygen production rate, water recycling efficiency, food production capacity, habitat structural integrity, waste processing rate, and the overall colony viability index. Let's trace some key relationships. Solar energy input has a positive relationship with both oxygen production rate and food production capacity, meaning more sunlight powers more life support. Access to subsurface ice reserves has a positive relationship with water recycling efficiency, offering a crucial buffer. Conversely, radiation exposure level has a negative relationship with habitat structural integrity, as high radiation degrades materials and stresses systems. Finally, a positive relationship exists between oxygen production rate and colony viability index, because without breathable air, nothing else matters. Understanding these interdependencies is vital for engineering a resilient colony. Build your Mars colony model and test its limits. What if a major dust storm reduces solar energy by 90% for 2 months? How would increased radiation exposure impact your habitat structural integrity over 5 years? Can your colony sustain itself if water recycling efficiency only reaches 90%? Designing a Mars colony opens doors to incredible careers. Aerospace engineers, earning between $85,000 and $160,000 per year, design the critical life support systems that keep colonists alive. Planetary scientists, who study Mars's geology and resources, make $70,000 to $130,000 annually, guiding where and how we build. Everything is a system. Model it, build it, simulate it, understand it. Visit ModelIt K12.com.